Can I ask a quick question about the BDI paper?
Hi, Mustafa.
Hello.
You just give me a second.
Oh, that was Alex.
Okay, go ahead.
So there's sort of like, I was looking at, because you say that they, what is it? You can sort of just pick the first element of the cache and use that as your base.
Mm-hmm.
But then couldn't you just, like, essentially you could just infer that the first delta will always be 0 from that. So you could just ignore it and just like have a, yeah.
Alex, you're absolutely correct. This is just a small optimization that at the time when we're writing, not to complicate things we didn't write about, but you're absolutely correct. If you make an assumption that your first base is going to be the first element in the cache line, then your first delta 0 is always 0 and you don't need to store it. But that's the fact that you're using the first base as the first value is a heuristic. So we try to describe mechanism in generic terms, but if you pick these heuristics and stick to it, then you can save on space. So whenever I open source the code for BDI, we actually make this optimization. Make sense?
Gotcha.
Yeah.
So is it included? So is it included in the benchmarks in the paper or no?
I think in their, good question, it's been a while. I think it is actually in the actual runtime and the performance, it is with this optimization. But the description is, try to keep it generic, because the problem is when you submit a paper, people might be very critical about you tied to particular heuristics. So like, oh, you make this, compressed sizes only work with this heuristic. What if it doesn't work, and things like that. So it's described without the optimization, but it's actually in the results.
Okay.
Okay. Okay. As usual, we'll wait until 1:10 so that everyone would join. I'm still here. If you had any questions, you can ask right now.
Now that the deadline is due, what do you think is the biggest weakness of your paper?
The biggest weakness of that paper, if you don't look at the follow-up papers from me and others, there are two. One is fragmentation, right? So that fragmentation was not properly addressed here, although it was addressed in follow-up works from Wisconsin Medicine. And another one is how to do a proper replacement for those caches, because you might be in a situation where you need to replace multiple blocks and things like that. And that I addressed in one of my own papers later on. There are some other more of, I wouldn't call them fundamental things, more like engineering challenges. It's how would you, for compressed caches, for example, how do you handle and engineer them so that like you might have more extra read and write ports, things like that. So if you actually try, if you know the design of the real cache, like Intel AMD ask those questions, right? They might ask something, but it's hard for us to judge because I don't know how their cache is designed, right? That's proprietary information. So that's more on the engineering end, but on the fundamental end, fragmentation is part of compression always, no matter what kind of compression you use. And another one, replacement, right? Everything was fixed size, now everything becomes variable size, so things becomes more complicated. I was able to turn this weakness into strengths in the cache-aware management policies paper called CAMP that we published, I think, HPC 2015. On this one, I actually show that compressed information can be useful for smart replacement policies. So we not only solve how to manage multiple evictions, but we also show you can actually do better replacement policies with compression information. One question I have, guys, to you. So did everyone figure out your group, and your project, more or less? I get some questions. I try to answer to all of them quickly. I just want to make sure that everyone has a project and you can submit your project proposals today. If you don't, please email me. Today's lecture will consist of two uneven parts. First, we're going to spend time and finish the material about memory hierarchy and caches from the previous lecture. Still substantial pieces, around 30 slides on that topic. And after that, we're going to start to talk about main memory, and we'll start the DRAM topic. I guess one small bit of announcement as well. So there is a little bit of a delay with reviewing your second reviews because the TA is having HPCA rebuttal this week, but it should be done like end of this week or early next week. So sorry for the delay. Okay, I guess let's start. So where we stopped last time when we talked about the caches, but before that, so just a reminder, deadline October 1st for the project proposal. You know, something along 1 to 2 pages, even 3 pages is fine, right? And as usual, please turn on your cameras if possible, and don't hesitate to interrupt and ask me questions. And it doesn't need to be in the chat. You can actually just mute yourself and ask the question. Okay.
I turned on my camera, but I'm using a second screen, so my laptop's camera is basically facing the wall. So sorry about that.
Yes. Okay. So what we're going to talk briefly is, okay, good question in the chat. Okay, no problem. So it's like if it doesn't work, it's just, it helps me if at least some of you turn on your camera, so at least you can see the reactions. Okay, so we covered a lot of things in caches. So today we're going to continue that topic. We're going to talk about the writes. So remember with caches, read and write are a little bit disproportional in the sense that read is on the critical path, right? You probably noticed that when when you read BDI paper, that leads to the situation where decompression and compression has different importance, right? Because the one was on the critical path was not. That's a general problem with caches. Reads on the critical path, so you always optimize for reads, but writes needs to be still handled properly. So one question related to writes is, well, when the modified data in the cache happens, when do we actually go and update everything else down the stack? So, and there are two strategies. One is write through. So the minute the write happens, you immediately propagate all the information down to the lower level of the cache hierarchy and all the way to the memory, right? So try to make it as fast as possible. Another strategy is like more lazy strategy is essentially it's a write back. So only when the block is actually evicted from the cache, right? Then it's written back. All the time before that, that modified data happens in the cache and you can read it in the modified format, but the memory and lower layers still have the old unupgraded data. Both strategies have their pros and cons, so I briefly cover that here. So essentially, write back, the main advantage, as you can imagine yourself immediately, is that you can combine multiple writes to the same block. So imagine you take the whole cache line and you update sequentially every 4 bytes in this cache line, right? So it means that you first update 4 bytes and another 4 bytes and another 4 bytes. You don't want the first update in this cache line trigger the write back, write through type of write back into the hierarchy, because immediately you're going to change another piece of data in this cache line. So instead of having, 16 writes into main memory, you want to have just one. So write back and combine multiple writes. And remember that cache line, if it's something frequently accessed in your hot data set, it might be updated many times. So instead of updating memory every single time something is updated, you only update it when you really have to, when the data leaves the cache. So it potentially saves bandwidth between cache levels and saves a lot of energy, right? But if you handle write back, you need a bit in the text store indicating the block is dirty modified. So essentially it complicates the cache design. So you need at least one extra bit in the text store to say whether this cache line was already updated or not. So you know when you evict it, what to do with it. Another alternative is write through, which is much simpler, right? There's nothing needs to do. You just immediately, at the minute you write, you just propagate everything down the stack. But, and all levels are up to date. So from the perspective of consistency across the whole memory hierarchy, it leads to a simpler cache coherence design. So there's no need to check whether their nearby caches has the same block with their most up-to-date versions. But it's clearly for something like shared caches that can lead over to very, extra bandwidth usage, and there's no right combination. So performance-wise, this design is worse. Okay, any questions here? Okay, so that's essentially the major part on how we're handling. So that's the first parameter, write back versus write through caches. Then another problem allocated is how do we allocate data in the cache on a write miss, right? So essentially, what does it mean? It means if I want to write in a cache line, store it, and the cache line doesn't exist, what do we do? And there are, again, two strategies. You either allocate data on write miss, right? So you bring the data. How that can happen? So imagine you are writing into a cache line, you had a store instruction, right? And store tries to say something, but that cache line is gone. It's not in the cache. The question is, should we bring it in or not, right? And there are two alternatives. One is no allocate to write, and another one it is. So what's the difference?
So this is for a write back case? Or?
This is not the write back. That's a separate problem. The write back is what to do when the cache line is modified, immediately or not. Here the question is, if I write something and that something is not in the cache, what should I do? Okay, so those are two different things, but related to writes in general. I'm just trying to cover all aspects of writes right now. There are three major aspects. So one is write through write back versus write through. Another one is called no alloc versus alloc. That's how people usually call it in caches. When you're going to read about cache designs, you're going to see they say either no alloc versus alloc. That's what it means, right? Allocation versus no allocation. So allocate and write miss can combine writes instead of writing each of them individually to next level. So allocate and write is simpler because write misses can be treated the same ways as read misses. So there is no need to treat them differently. On the read miss, right? It's missing in the cache, you bring it, right? There's no discussion here. So, but allocation on a write miss, one problem, it requires potentially transfer of the whole cache block in the naive implementation at least. So what does that mean? It means I might write just 4 bytes, right? But I have to now bring the whole cache line, right, to pick there. So on no allocate, It conserves cache space if locality of writes is low. So it can potentially lead to better cache hit rate, but it has some downsides as well. Yeah. So what are those other aspects you need to think about? So what if the processor writes to an entire block over a small amount of time? And another question, is there a need to bring the block into the cache from memory in the first place? That leads to the idea of called sub-blocking, right? So for example, instead of bringing whole cache lines, can we bring like small blocks, 4 bytes or 8 bytes, right? Those are all open problems. People propose different solutions to that. Just to let you know, to the best of my knowledge, existing caches don't do any form of sub-blocking. Most of the designs I know, they just bring the whole blocks, right? But whatever I discussed, write through versus write back, and alloc versus no alloc, there are caches that pick both choices. So you would, when you're going to look at different designs, you're going to find caches that have different policies. Even across different layers, they might have different policies. It's all based on the trade-offs that designers figure out for that cache. Okay, this is how we handle writes. So now we are ready to talk about cache performance. And we're going to look at cache performance with respect to different parameters that it can change. Cache size, block size, remember associativity. This is something we covered in the previous lecture. Cache size, block size, associativity. And then replacement matters, obviously. And insertion placement policies also had a strong effect. And we're going to look at the cache miss hit rate, which is a good indication of cache behavior, but not perfect. I'm going to talk today about when this metric is not great in some cases, but in most cases, it's actually a good metric. So if you reduce the number of misses, that usually improves performance. Okay. Anyone can speculate right now before I'm telling you about that, when can be the situation that you reduce the miss rate, like the number of misses reduced, but performance doesn't improve or barely improve. Any theories? I'm trying to wake you up. I'm going to give answer later in the lecture, but I just want to force you to think.
My guess is that like you're somehow worsening the performance down the hierarchy. So like you're either getting more memory accesses somewhere or something.
Not necessarily. I'm looking for even simpler situation. There are really situations, it's not like making it worse, but it can be that it doesn't really bring a lot of benefit.
I see.
Think about it from this perspective is you had one access to memory, like cache miss, and access to memory, say 100 cycles, another 100 cycles. Compared to compute, this is 1-2 cycles usually. That's like peanuts, right? Sorry. So the question is then, how is that possible that this thing doesn't help? Okay, I'll let you think about it. If someone comes up with an answer, let me know. We'll keep moving, and eventually you're going to see the answer in the slides. Okay, let's look at their cache size and how it affects things. So larger always better only works up until a certain point. It's the same with caches, right? So cache size is the total data, not including the tag capacity. The more you have, the better you can exploit temporal locality, but it's not always better. Why is that? Well, when you make it too large of a cache, it adversely affects hit and miss latency, right? Smaller is faster and bigger is slower. So essentially there's a trade-off here. If I make a larger cache, then I can feed potentially more data in it, but irregular accesses to the cache becomes, slower. So that's where the trade-off is. And that's depending on layer of the hierarchy and your data sets, the answer what's the optimal can differ. So too small of a cache doesn't exploit temporal locality well. It's useful data just replaced too often. So essentially what really critical to understand the behavior is a so-called working set size. So working set size is the whole set of data that the execution application references within a certain time interval, especially where it was used frequently. So that thing you want to get into your in your cache. As soon as you get into the cache, you get the rest is diminishing return, right? So really, that's what you try to. Want to get the minimal size that would make it fit, right? And after that, you just get variable benefits on there, on the latency. So the hit rates would improve, but essentially, if you look at cache size versus hit rate, you're gonna have amazing improvement here. Okay, so you're gonna get amazing improvement here up until a certain point where the most of the working set size fits, and then it plateaus, right? So the performance doesn't improve any significantly after that. So the problem is that there are infinite number of workloads, right? They all have different working set size, so it's very tricky to find the right capacity. So people try to find some compromises.
I think you're cutting off, and it's not just me because I see other people moving. So,
what did you say, Mustafa?
I think you're cutting off. I'm not sure if it's just me because I can see the other people moving, and like your video just gets stuck for a few seconds.
Yeah, I know there was like some lag for a second, but can you hear me now well?
Yeah.
Do I need delays right now?
No, right now it's fine.
It happens sometimes. I can't really do much about it, unfortunately. No matter how much you pay for the internet, they still have lags. So, okay. So that's cache capacity. It's relatively straightforward. You're trying to get the most of your working set fit in the cache. So when you optimizing performance of your workload on CPU or GPU, that's the first order thing to think. What is your really critical working set size that you access frequently? And then you look at the memory hierarchy exists, and then you need to think where it fits, which layer of the cache, right? And then you try to optimize it to fit nicely. That's what usually people do when they optimize things like matrix multiplication and things like that. Okay, second parameter, block size. So as an architect, that's another parameter that's within your hands. Block size is the data that is associated with an address tag. So when we talk about block size or the line size, this is when we say 64 byte or 32 byte or 128 byte. I've seen even cache lines of 256 bytes in some early GPUs. So it doesn't have to be necessarily the unit of transfer between the hierarchies, although in most cases it is. People can use sub-blocking of different forms. But essentially, the trade-off, again, remember that a lot of things in architecture is about trade-off. Like if something could have an optimal parameter, it wouldn't be a parameter. You would just select the value to be a certain number. So two small block sizes, you want exploit well spatial locality. Remember, capacity is about temporal locality, trying to keep within time limit as much data as possible. Cache block size is all about spatial locality. So if I access 4 bytes, there's a high likelihood the nearby bytes would be also useful. So if it's too small of a block, then you don't bring this data in. I would need to make another extra access for this data, and I would have to also have large tag overhead. Because the smaller the blocks, each of them need an address, right? In the address tag. Remember, we store address tags separately from the data in the cache. So under the same capacity, say 1 megabyte, if I go through, instead of 64 byte block into 32 byte block, I would need twice more tags to store. And tags are expensive, both in terms of storage and in terms of complexity of the design, right? Also, the more tags you have, the longer it would take to search through the tag storage, right? So obviously it's going to increase the general latency. If I had too large of a blocks, so that within the same capacity leads to fewer numbers of the blocks. So if I had 1 megabyte, if I keep increasing the block size to say 1 kilobyte, then I only had 1,000 blocks available. So I had the total now blocks less. So that can hurt temporal locality because the number of different objects I can store at any time is smaller, right? So it can lead to waste of cache space and bandwidth and energy if spatial locality is not high. Because spatial locality and temporal locality, despite they're both called localities, they had different sources, so they might not necessarily align. So the typical curve you're gonna get from the block size, it keeps going up, up, and up, and then at some point you get the maximum benefit, and then it goes down. So in most cases, there is this optimal block size that covers most of the applications and their localities. But again, even though for CPUs, it's usually just 164 byte for many reasons, historical and evaluation, empirical. Say for GPUs, that size would be different, the optimal size, because they had much better spatial locality. in contrast to CPUs on average. So how can you deal with large blocks? There are different optimizations that you can do, and you can read about that in the spare time. So essentially one is the critical word first. This is essentially when you bring the data, what you're trying to do is to bring the data that's really, really needed first, because the read, like say you had a cache miss, and that read wants to bring the data. You want to bring really this 4 byte, because this 4 byte are really needed. They're needed for me to finish the load instruction, right? But if I'm going to wait until I bring the whole 64 byte, I might delay it. So people implemented a technique called critical word first. It means you first bring the first value that you really need, and then the rest of the cache line, right? So there is a priority mechanism that allows to bring the critical bits first. Okay, and as I said, large cache blocks can waste path bandwidth. There are a lot of optimizations you can do, which is sub-blocking, where you track different pieces and bring different pieces. And you can think about when this is useful or not. I don't want to go too much into that. Okay, so associativity. So how many blocks can be present in the same set, right? So what is the trade-off here? Again, large associativity versus small associativity. So the larger associativity, the lower miss rates will reduce the number of conflict misses. Remember, those misses happens because you would love to keep that, but there's only that many slots for blocks that happen to have the same address, right? So you cannot have too many. So the more associativity, the more I can have, the more flexibility I have. But the larger associativity, the higher the heat latency and area cost. Remember when I showed the circuit, RAS circuit design for associativity, you've seen the higher associativity I have, the more parallel comparisons I need to make with different addresses, right? So it clearly increased the area and their latency overhead to deal with. Because no matter whether it's hits or miss and whether you resolve conflicts or not, you always pay the extra price for high associativity. Whether you benefit from it or not benefit from it, the cost is permanent. Small associativity has definitely lower cost and simpler design, lower area overhead, but you get lower heat latency. And that is extremely important, especially for L1 caches, right? So L1 caches are typically like 4-way caches at least, because higher associativity there would increase the latency dramatically, but you cannot make them direct map and as in the regional caches, right? So essentially the curve for associativity is like that. It always improves, right? So essentially the cache where you have no limits, like your associativity essentially matches the number of blocks in your cache, is the best from the hit rate. But what that limits you is the ultimate performance. So hit rate improves, but remember, it doesn't mean that performance improves, right? So this is associativity to hit rate always improve, but then there's a diminishing return and performance goes down eventually because the hit latency goes up, right? So the performance might go down because of that. So one question is to you guys, is power of 2 associativity required or not? You're always seeing 2-way caches, 4-way caches, 16-way caches, 30-way caches. You never seen 10-way cache normally. So is this required or not? And yes or not, try to justify your answer, and and then try to justify why we usually see powers of 2. I guess I already hinted you the answer, but you still need to explain it.
Okay, I guess it's not like required per se, but like if you don't make it a power of 2, then addressing becomes really hard. Like right now, you can literally just take like some amount of bits and use that as like to figure out which set it's in. So like if you want
in the right direction, Mustafa, but but I think it's still a little bit incorrect in the sense that you say it's making it more complex. First, the answer is obviously is no, it's not required. But say if I do a 10-way cache, would it be more complicated than 16-way cache?
Yes.
Why would it be so?
Well, because you need to figure out, like, given an address, which.
But it's the same for 16-bit or 10-bit. Like I would need to figure out the same address.
Well, if it's 16-bit, I can just take, like, I can discard the least significant 16 bits and then use that to index into the correct, like, Find an index and
trying to get closer to that. So essentially the short answer is like a 10-way thing. You would need to use the same number of bits in the address into mask as in 16-bit, but you don't fully benefit from the extra bits, right? So in terms of like essentially what you would have to do if you had 10-way cache, for example, you would still have to reserve the same fixed number of bits, say 4, as for 16-way, but 6 of the states you won't use, right? So essentially that would be wasted completely.
Yeah, like in my head, I was trying to I guess I was trying to not waste space. So I was imagining some mechanism where like you didn't have any extra bits. You like somehow dynamically figured out which side it's from.
That's hardware, remember, that would be more costly than wasting.
Yeah, that's what I was talking about.
Yeah, so in reality, no, nobody's gonna add extra logic for that. They would just waste not useful ways, right? But that would be a waste. So people usually don't go for that. Tag beats are extremely precious and limited, so people are very careful with using them. Okay. Okay, the classification of cache misses. So there is a famous paper that calls 3 Cs of the caches. So essentially, caches have 3 types of misses: compulsory, capacity, and conflict. All starts with C, right? So what are those misses? The first one is so-called compulsory misses. This is a first reference to an address that was resulting in a miss. So essentially, you have no way, or almost have no way, to figure out that access would happen. So it's a first ever miss of that kind. So you have to handle it, right? Those are one of the hardest to deal with. So subsequent references should hit unless the cache is displayed for some reasons described below. So it's essentially, it's like a warm up. Like you've never had anything in the cache, then you bring something new and that results in a miss. Capacity miss. So cache is too small to hold everything needed. So it's essentially defined as the miss that would occur if you had a fully associative cache with optimal replacement of the same capacity. So you had a full flexibility in the cache, and essentially you had the smartest possible replacement. And if it still happens, that means it's just you didn't have enough capacity, right? So you just really, so for example, if you had, I don't know, 2 megabyte cache and then your working set size is 10 megs, it doesn't matter how smart you are with replacement, right? So if every single element touch once and then you go in circle across this 10 megabytes again, there's nothing you could physically do. I would say not nothing, but there is, it would lead to potentially a capacity miss. There are certain things you can do like prefetching, we're gonna talk about that. But otherwise, if you cannot detect that's coming, right, you really nothing you can do, it's a capacity miss. A conflict miss, it's defined as a miss that is neither compulsory nor a capacity miss, which is usually mean my cache is not optimal in some sense. It's either doesn't have enough associativity or its replacement policy was not smart. So it could have been in the cache, but it had ended up being evicted because we did something inefficient in the cache. So how can we reduce each miss type? So compulsory misses, very short answer, caching cannot really help. So caching can't really do anything with compulsory misses. There are other techniques we're going to talk in this course, but not the caching. So essentially caches just take this as given. This is a part, but remember compulsory is usually a small part of the misses compared to everything else. Prefetching can help in this case. So conflict misses has more associativity. There are other ways to get more associativity without making the cache associative. I'm going to mention this one of the ideas today, because associativity becomes costly, right, as you can see. But there are ways to get better resolution of conflict without going into this domain. We're going to talk about something called victim caches very briefly, better randomized indexing in the cache, some software hints. There's a lot of prior work, like hundreds of papers on that. And capacity misses, you try to utilize cache space better, key blocks that will be referenced soon, better software management, all of that can help with the capacity misses. So essentially, when you try to improve cache performance, there are 3 fundamental goals. You try to reduce the miss rate. Obviously, the fewer misses, the misses are costly, the better it's for performance, right? And reducing miss rate can reduce performance if more costly to refetch blocks are evicted. Reducing miss latency or miss cost, and reducing heat latency or heat cost. And you try to get most of that nicely balanced. the above three together all affect performance, so you need to find good compromises when you fix one such that you don't hurt the other ones too much. Remember I said you can keep increasing associativity, it keep only improving the miss rate, right? But that comes at the cost of both hits, latency and miss latency, which is significant. So here are some different approaches that some of them I covered, some of them exist. So I will just leave this list for you to study if you're interested to learn more. So I'll show you some examples of how to reduce conflict misses in a cheap way. So like back in the day where hardware was very expensive, more expensive than right now, people tend to be more creative about how to increase performance. So like a lot of interesting ideas came up, including the idea of a victim cache. And the other ideas are hash randomized index functions, pseudo-associativity, and skewed associative caches. I'll show you a few examples of those. So what is a victim cache? And this is the paper that was proposed by Norm Juppy like 30 years ago. So back at the time, most caches were direct map. Associativity was considered too expensive, right? So people just use direct map caches. So what Norm suggests is to use a small fully associative buffer called victim cache to store recently evicted blocks. So what's the key idea? So think about it. Instead of trying me to add an expensive feature, associativity, across the whole cache, let's create a buffer where everything is recently evicted, not go all the way to the memory or the next level cache. It stay in this small buffer for a while. And if you happen to be, you know, a victim of a needed eviction, I can grab you back very fast from that buffer. Why is it a good idea? Because it gives associativity not per set, right? But it gives it to the whole cache. So my conflicts might not have across the whole cache. I might have just a few sets where I had conflicts and everything else has no conflicts. But if I do associativity, I kind of trying to get rid of conflict misses, right, on each set of my cache. This thing, instead of fixing the problem for everyone, even though there are only a few people, like say, or a few sets have it, right? Then that's the thing. It's like, you know, giving someone a cure for a disease, like a big population where only, I don't know, 1% of the people actually benefit from the cure, right? Everyone else gets it. It's like it's costly and might have side effects, so it doesn't really worth it. So it's the same idea here. So we can avoid ping-ponging effects of cache blobs mapped to the same set, and it handles it very cheaply. You just had a small buffer, fully associative, but it's easy to implement, and it's relatively nice because, you know, this thing almost doesn't change. This cache doesn't change. You just add one site structure that just communicates with direct map cache, and that's it. Yeah, so there are other ideas such as better randomization and index functions. And those can be more complex to implement, but they try to redistribute blocks across the cache more evenly, so they're essentially the conflicts are more rare. Okay, so I'm not going to talk too much about pseudo-associativity. It's just in the interest of time. You can read about it if you're interested. It's just another technique to get high associativity without actually pulling the full price of it. Another very interesting idea is from Andrei Seznek called A Case for Two-Way Skewed Associative Caches. Again, one of the older papers, but very fundamental. Andrei Seznek is like, there are some people that generate a lot of really cool ideas in computer architecture. So Andrei Seznek is essentially the inventor of probably the most efficient branch predictors that, to the best of my knowledge, still use at companies like Intel and AMD. And I believe some other chip makers, they like, I collaborate with another company recently and they were working in branch predictor. And when I talk to the architects, they're still using ideas from this paper. So it's like, it's something you invent that stays being very, very fundamental. So, so essentially skewed associative caches is that instead of having a basic two-way associative cache where same index functions used for both ways the same way. So everything is symmetric, right? That's how it's used right now. What he suggests is to has a separate function f that that's used differently for different cases. So that allows when you do mapping, right, you don't just do the linear mapping, use some fancier function that would distribute sets differently across the ways, right? So that makes sure that you don't have as many conflicts. So, so essentially the idea here is by reducing conflict misses by using different index functions for each cache way. It turns out to be relatively cheap, but reduces conflicts significantly. So benefits are that the indices are more randomized, but without full randomness, right? Because of just hashing of some sort, but you get most of the benefit of randomization without using random numbers, and they're better distributed across sets. So it's less likely with this design that two blocks have same index, especially with strided accesses, so it reduces conflict misses. The only overhead really is additional cost of a hash function. So essentially, if you come up with a good hash function design, right, and you put that hash function in front of the circuit when you do address calculation, that's it. One important thing that it also needs to be latency optimized, because remember that resolution on their, hit versus miss, it affects the critical latency of their cache accesses, right? So whatever this hash function does is added to the overall latency. Okay, so far I'm mostly focused on the hardware techniques, right, on how to handle latency, but people in software were very proud to deliver a lot of smart techniques to reduce cache latency as well. What they do, they either restructure data access patterns, restructuring data layouts, do techniques like loop interchange, data structure separation, merging, blocking. I think some of these software techniques you might actually have seen in some of the courses. If you ever had an assignment to, say, implement matrix multiplication right on your own, like when I taught second year undergrad class at CMU in CS department, we gave this as an assignment, right? And one technique we tried to improve performance of matrix multiplication was tiling, right? So you try to tile the matrices you multiply to the level that would nicer fit into your last level cache. Okay, so those techniques are also powerful. They play around essentially the limitation that your hardware has. So first is restructuring data access patterns. So idea is to restructure data layout by knowing the patterns. This is something I'm teaching in my undergrad compiler class. So for example, you need to understand column order versus row major order. So for example, something like this, xi plus 1, comma j, follows the element aij in memory in the column major organization. But if you had ij plus 1, this is very far away from I plus j in most cases. So that's important how you can restructure your code. So for example, if you had semantically similar code, this code is going to execute poor on the systems that have column major organization. And if you actually gonna go in the loop in a different direction, this way, that's gonna actually execute better because that's about how the data is stored, right? This technique is called loop interchange. So this is one way, like the most simple way to change things. This is simple because loop iterations don't have dependencies across iterations, right? So it's just very straightforward to change the dimension because they're all independent. You can compute sum in any order you want. But in many other cases, things are more complicated than that. So there are other optimizations such as loop fusion, array merging that exist to optimize things. Yeah, so there are all these unknown questions here that people try to figure out: how to deal with multiple arrays, how to deal with arrays where sizes are known at compile time, what are they going to do about those? Another technique that I mentioned is loop blocking. So you divide loop separating on arrays into computation chunks so that each chunk can fit into cache. So it's avoid cache conflicts between different chunks of computation, very efficient, but there can be still self-conflicts in a block. Those you can really, those things are very hard to do at compile time. Usually hardware needs to help with that. So essentially, another example of restructuring data layout is something like that. So look at this code, right? You had a struct node. It has a pointer to the next field. So it's like a linked list. It has a key, and it has two big arrays of chars, name and the school. And essentially, this is the piece of code you write to traverse this thing. So you had while node, then you compare the two keys, and the node keys and the input keys given. And then you might access other fields of node, might not, and then you had node equal node next. So assuming a huge linked list of 1 billion nodes and different unique keys available for each node, what can you do here? Why does the code on the left have poor cache hit rate? What do you think? Why would it have a poor hash hit rate?
I'm guessing that like the name and school are fetched in because they're all part of the same struct, but like you don't use them most of the time.
That's a correct answer. They're huge, right? But you not necessarily need them all the time, right? But you're going to bring them, so they're going to kick out other useful data. So other fields occupy most of the cache line, even though they're very rarely accessed. Sometimes they might not access at all. So techniques you can do, you can slice the struct nodes into different structs in the compiler itself to optimize for that. So it's like one way is to do what I showed in this slide. So in struct node, you had a substruct called node data where you put this rarely accessed field. So essentially here, I'm gonna mostly iterate over this data structure, right? And I'm only gonna use that interaction when it's really needed, right? But what I'm gonna store, say it's a 32-bit machine. So right now, this is 32-bit, this is 32-bit, it's another 32-bit, right? And before I was storing like more than 500 bits, 500 bytes, sorry, because there was like two fields, both of them were 256 bytes, right? So you just separate frequently used fields and pack them in a separate data structure with whatever is accessed infrequently. And I think I get already answer to this question, who should do it? There are many ways. So sometimes you can do it manually. Sometimes you can rely on the compiler, although compilers usually cannot do it without some help. Hardware, it can be very difficult for hardware to do it. And you can also think about how can we determine what is frequently used versus what's not. And we had some students in my group that actually works on these problems, like how to actually compress those data structures efficiently or restruct things efficiently, and how to detect frequently used fields at runtime. Okay, this is an interesting research problems. Okay, so we covered this stuff. So miss, latency, and cost. So what is miss latency and what is miss cost is affected by? So to answer these questions, the first questions we need to answer is where does the miss get service from? It can service from local versus remote memory. It can be serviced from different levels of the hash hierarchy. It can be raw hit versus raw miss in DRAM. So today we're going to touch DRAM a little bit. You're going to learn about raw hit, raw misses if you didn't know before, right? Based on the DRAM organization. Like latency to DRAM are not one fixed latency. They can vary depending on different situations, like 3 or 4x. So that can vary. So that affects miss, latency, and cost. And how much does the miss stall the processor? So remember that question that I asked at some point about how is it possible that I reduce the miss rate, but performance doesn't improve significantly? So the first question here kind of answers this. So it says, is it overlap with other latencies? So essentially, I may have one miss and another miss, and they can be almost back to back. So the latency, no matter how large it is, can be almost fully overlap. So it means that the extra miss that happens might not really slow down things a lot, right? So think about it this way. If you access, say you access something like a cache line, right, a data structure element, and then you had a smart technique that knows that you're about to access the next cache line, right, say prefetcher. They're going to prefetch that other line almost immediately after access the original line. What's going to happen, both latencies are going to overlap, right? You're still going to consume memory bandwidth, but if you have spare memory bandwidth, it's not going to increase the latency, almost, okay? Is this clear? So this is the way, even though you might have fewer misses, And that's very frustrating. Sometimes graduate students work on the paper for months, implementing something simulated and say, okay, miss rate should improve. Then it is improved in the first simulation. Then they finish their performance model on their simulator, run experiment again, and yes, miss rate improved, but performance doesn't. And then you start to look at why, and it happens, well, your technique that you invent only helps on the secondary misses, right? The one that comes with something else, right? Not individual isolated misses, so performance barely improves. Okay, and I've seen this, it can be quite frustrating because usually you feel like if I improve miss rate, performance should go up, but it's not always the case. Okay. Yeah, and that theme that talks about that extra parallelism is called memory level parallelism, or simply MLP. So here on the graph, you see isolated miss, where the full latency added to the latency of success. And you have two other misses, B and C, that are parallel, and you see they overlap a lot. So there's only some small extra latency added from an extra access. So memory level parallelism means generating and servicing multiple memory accesses in parallel. There are a lot of techniques that was invented to help with MLP. One of those is out-of-order execution. MLP can vary. Some misses are isolated and some are parallel. And it's affected by how you write the code, your software stack, your optimizations, and hardware. A lot of parameters that goes into that. So it obviously affects performance. So traditional cache replacement policies were pretty much ignoring that aspect. They were just focusing on reducing the miss rates, similar to those gradient students that were, negatively affected by, by miss rate improved but no performance. But when people realized that MLP is important, especially when out-of-order processes start to ship massively, so that was keep coming. So people noticed that this implicit assumption that reducing miss count reduces memory-related stall time is not always correct. And MLP essentially breaks these assumptions. Yeah. So here is one example where you can see that even ideal replacement, sequential, that doesn't take MLP into account, might lead to suboptimal performance. So essentially, here you can run their animation, I guess, here on your own, but I'll just briefly describe. So Ballad is optimal. It's considered to the optimal sequential replacement policy. Ballad is optimal knows the accesses into the future perfectly. So imagine you run an application once, recorded the trace of accesses, and then you replay it again and you know perfectly all the accesses, right? That's considered to be the optimal replacement policy, but it's unrealistic because it needs to perfectly know the future. Well, funny thing in this example is that it was used for many, many years as an optimal policy. It turns out in the presence of MLP, it's not optimal anymore. So essentially, let's say we have a fully associative cache containing 4 blocks, right? So at the beginning, so the Ballad is optimal policy. So let's say at the beginning cache have P3, P4, P3, P2, P1, right? So, and then you had new blocks S1, S2, and S3, right? So what's going to happen, you're going to keep bringing them in, right? And they're all going to generate misses. And then when you're going to come here, you're going to keep, essentially, that's essentially the sequence of the accesses you're going to have. So that's what you're going to originally have, right? Hit, 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 miss. And then you had 4 hits here and then 4 misses. So you had 4 misses and 4 stalls. And that's what you would do if you know that perfectly essentially all the memory accesses that come in. With MLP-aware replacements, you can actually be smarter than that. So you know that those misses here, S1, S2, and 3, are more isolated, more important. So what you're trying to do is essentially you're trying to keep S1, S2, and S3 instead of P1, P2, P3, and P4. So the number of total misses is actually higher, right? You get 6. But the number of really long stalls is reduced because both stalls are now aggregated, right? Because having more misses here that are close by is actually better than having more of the isolated misses. So this is one example showing how even the optimal replacement policies based on counting the misses might be wrong in the presence of memory level parallelism. Okay. Any questions about this example? So you see the number of misses improved, but the number of big independent stalls actually reduced. Yeah. And that again, those ideas and the problems come up when people start to work on multi-core systems, out-of-order engines, right? So for a long time, that considered to be that valid is optimal is the reference point. You cannot beat it. It's the ideal. Actually, my cache-aware, compression-aware replacement policy that I came up, like I think 5 years ago, I also demonstrate something similar. I show that the valid is optimal if it doesn't know that it's not aware of the block size with compression, like the compression you read about in BDI paper, then it was going to make suboptimal decisions. And I show you can do smarter decisions if you actually know the compressed block size. Right. So similar to memory level parallelism, block size awareness is helpful, right? Okay. There is multiple papers published on this topic, so that here's just one reference on what you can read about it. And that essentially ends, I guess, the first hour of today's lecture. So we pretty much cover, I know it was a little bit rushed because it's a huge topic, memory hierarchy of caches. You can have, like I had some of my friends that teach in the full courses on just memory and caches, right? But I thought you get yourself a little bit more familiar about how caches operate, right? And what are the parameters that affect them from the hardware end, from the software end, and what kind of optimizations can be done with them. And if you're interested to learn more, you can read some of the reference papers that I have here, okay? And we are gonna have now a 10 minutes break. And after that, we'll continue to learn more about memory and DRAM. Okay, so see you guys in 10 minutes. Okay, guys, welcome back into the second part of this class. Today, we're going to talk about main memory now. Again, please, if you can, turn on your videos and we'll start. Okay, so we talk about caches, which are interested, but obviously a lot of us I've heard about caches already, but main memory, I noticed that way fewer graduate students, even specialized in computer architecture, know a lot about. So hopefully after today's class and partially next week class, you're going to learn way more about DRAM and would understand it much better now. Okay, so first of all, let's start with the review paper. So this is what you're supposed to review for next week. It's called ROCLAN, Fast and Energy Efficient in DRAM Bulk Data Copy and Initialization, which was published by Vivek Seshadri at Micro 2013. Okay, I hope you enjoy this paper. Okay. So we'll start with this basic question. Why is memory so important, especially today? And I'm teaching this class for the 4th time now, and I don't think nothing really changed with this question. It's still important, and like every year, it's only getting more important. So why is it so? Well, it's because the memory being a bottleneck in many cases, which people early times not always realize. So this is just one example on how memory can be important. So for example, this is the paper, this is the data from one of their first honor module papers on run-ahead execution. What you're gonna see, you're gonna hear the normalized execution. And the green part here is what time you spend on execution. And this part here, more than 55%, is L2 misses. And it's collected across a certain number of applications. The key takeaway here is it doesn't matter how you're creative with this green part, right, on the compute, if the memory is 55% of your latency. So very frequently, before trying to optimize anything on that, you should just look at memory. And that's what people didn't realize back in the day. And that's why memory still so important. So this is performance. So performance argument about memory is quite straightforward, but there are other aspects important about memory. So here I'm going to show you some relatively recent data from Bill Daly from Stanford and from NVIDIA. What I'm going to show you here is how the energy changes with the size of the data and different parts of the memory hierarchy. So this is a bit complicated graph, but not too complicated. Just stay with me. So essentially, this shows you the size dimension. This is like 20 millimeters in terms of how different objects look like. And essentially what you're going to see here is that how energy spent for different events in the absolute value. So you can get a feeling, what does it, you can think about power and energy in many cases as a currency for execute something. So if you only care about performance and everything is free, right, then you can always have, enormous amount of compute and cache and everything. But for everything, there is a cost, and the currency for this cost for compute is usually power. Remember, because there's a power budget for everything, right? We only can deliver that much power within this area. So this small green box here is a 64-bit dual precision add multiply, whatever joint unit. So you can think about it as the basic unit, 8-byte addition or multiplication. So this is your basic compute. Back in the day, on the technology available back then, doing something like that on a GPU would cost about 20 picojoules. That is your cost, right? So think about it, this is a cost. So then how about memory transfers of different sorts? So if you use a 256-bit buses that are very common, and you say try to access an 8-kilobyte SRAM. So SRAM is the technology that, as we learned, is used in caches, and this is a tiny cache. Then the access latency for that is 50 picojoules, right? So if you look at this, this is on the same order, right? Like if you had a relatively small cache. Things starts to be more complicated if we try to go for larger and larger objects. So for example, here, if you try to have like larger accesses to larger caches, you might have to pay 256 picojoules. So the further away the object is based on the distance, right, in terms of millimeters squared, the further it is. So you remember, if you look at the chip, right, you remember where the caches, I was showing you that some pictures where the caches were located. Some of them were distant. So if I need to go that far over the 256-bit bus and grab something, I don't know, 8 millimeters away, right, from where I compute. So the price for that communication alone is 256 picojoules. Okay, got it, right? So you see, if I need to go away from where compute is, there is already a price that is 10x of what is compute is itself. And that can be L1 or L2. But what is extremely worrisome, if you think about it, if I want to go and access DRAM that is off chip, just to read a single line of DRAM, it's 16 nanojoules, right? So think about it, 20 picojoules versus 16 nanojoules. So reading energy-wise, reading something from DRAM is 3 orders of magnitude more power than computing something. So when you think about DRAM, and you think about, oh my God, for performance, going to memory is 10x worse than going to cache. Remember that energy-wise, this is 3 orders of magnitude worse than computing, right? Or going to small cache. So this is why power aspect makes it even more complicated. And also transferring something from off-chip by itself is 500 picojoules, right? This is just any transfer. This is transferring the full DRAM row and activating. We're going to talk about DRAM, but that's the total cost of accessing one DRAM read or write. Okay. So I hope that you got a feeling on what are the dimensionality on different problems here. Okay. So the further away there is a very substantial amount of energy you need to spend to transfer it. Okay, those things I want you to remember. DRAM versus compute is 3 orders of magnitude in terms of energy. Okay, and there is another problem that exists with memory, which is reliability perspective. Most of us don't think about it because we usually don't get DRAM errors. Once in a while we get blue screen of death if you're using Windows machine or some similar equivalent on Apple machines, which might be related to DRAM errors that were not corrected, but we don't think about it that much. We just, reboot the machine and that's it. Hopefully there's nothing critical corrupted. Well, if you actually operate with millions of machines in the cloud like Facebook will do, those errors starts to be, noticeable, right? They're not something rare that happens. That's something you deal every hour, right? That's something that happens all the time. And what people noticed as you increase the density of their DIMMs, right, with which DRAM is surfaced, is that there is a quadratic increase with the capacity. So you want higher capacity, but the relative failure rate of the servers using DIMMs goes quadratically with capacity. So it's not like if it would be linear, that would be acceptable, but it's going quadratically. It means if I start to buy denser DIMMs, I have to deal with quadratic number of errors, which at some point goes over the roof and you have to deal with. It's not like companies like Facebook or Google do that because they're really curious about DRAM. They had to deal with the errors on the massive scale and they need a way to deal with that. Mustafa, you had a question?
Yeah, so the Y scale here is 0 to 1%. I'm guessing it's not 0 to 100%. Like that would be ridiculous, right?
What? I didn't get.
What's the Y-axis like here?
Y-axis is relative server failure rate. There is some metric there that computes the average probability of an error.
Okay.
Yeah.
So like, is that saying that at 4 GB chip, like that's almost 100%?
Yeah, it's essentially, if you look here, we go from 1 to 2, right? And that more than doubles, right? And then go to 4, and that's what the error rates go, what?
I'm just trying to make sense of that 1.0 there. Like, what does that mean? Like, does that mean like 100%? Like, if there's
no. It's some other metric. I don't remember. It's like if you look at this paper, what exactly it means, right? It's not 100% because that means everything would be a failure. But they had some metric. They converted with some like there's a weighted sum and like with some probabilities. So that's not 100%.
Okay, makes sense.
Okay, so that was one problem. The another problem is security perspective. I don't know how many of you heard about Rawhammer. I think a lot of my students heard from me about it, but it's a real vulnerability that the group I work with at CMU found. It's called Rawhammer, and I'm going to talk about it, but a very brief summary about that. Imagine that you want to, break into someone's apartment, and the way to get into that apartment is by you slashing into the neighbor's door, and you ended up getting into the room you want because there are vibrations from that door nearby that cause the other door to open. So this is what Hammer does. You hammer into the address space of your own rows on your VM, and by doing that in a certain tricky way, you can make the bit flips in the nearby rows, right? That allows you to actually get access sometimes to these VMs with root privileges. And this is not hypothetical simulation, it was done on a real system. So those are all different perspectives of DRAM and how it is important. So performance, energy power, fault tolerance, and security perspective. And I'll start with performance. And I'll start it with the question that I guess came out in the conversation of my friend Vivek with his friend at Stanford. So how the conversation was. So Vivek was a computer architect who worked with me at CMU in the same group. And he was talking to his friend at Stanford who was in the systems group there. And that friend came to Vivek and said, why is DRAM so slow? You guys spending so much time on DRAM, but it's so slow. And Vivek's like, really? Is it slow? Like we cut the latency to 50 nanoseconds now. And so yeah, 50 nanoseconds to serve just one request. Is it really fundamental? Or are you guys just bored and don't want to engineer it better? So the question essentially he asked, is 50 nanoseconds a fundamental to the DRAM organization? Can you do much better? How much better you can do, right? Why is that the way it is? Why we have the spec that says 50 nanoseconds for the access latency? And this is what I will try to cover in substantial detail in today's lecture. Hopefully you will learn today a lot about DRAM. We're going to see why the latency is the way it is, right? Okay, so we'll try to learn and understand DRAM better. So what is in here? Problems related to today's DRAM designs and solutions proposed by the group I work on for a while that does a lot of research on DRAM. So we'll start with, probably today we won't be able to cover everything. So today I'm going to cover the DRAM basics and DRAM internal organization, hopefully. And next time we're going to talk about different research papers related to DRAM. So we're going to talk about what is DRAM first. So DRAM, as I mentioned before, is dynamic random access memory. So the key thing, it's memory, right? What memory means is an array of values, right? Organized in a certain way. So what's the most primitive API to deal with memory? It's read and write accesses. Read just wants to get the value based on a certain address, right? And write, put the value that you want to store into this address. So what does the random access means in this DRAM? It means that any location would take the same amount of time. That's why it's called random access memory, okay? And dynamic means actually nothing positive. Usually dynamic is a positive thing. Here it's not really that positive. It means that the data needs to be constantly refreshed. Remember, we covered that a little bit when we talked about DRAM before. So refresh is needed. So DRAM is in pretty much any systems you would use today, from the smartphone to the small IoT devices, laptop, desktops, supercomputers. So why DRAM? Why do we use DRAM? Why not some other memory? If you actually talk to companies like Samsung or Micron that does manufacture memory, they try dozens and dozens different potential technologies, and they all fail because of certain reasons. And we'll try to understand what these reasons are. So let's look at this von Neumann model that we had, right? Remember, in von Neumann model, there's no caches. Cache is an optimization. There's a processor and a memory, right? There's a program that executes stuff, and the program needs to read data periodically. And essentially memory supplies this data, right? So when you do T1, read data 1, you get the value 4. you get T2, read data to so on. So essentially, if you execute this program, you're going to get 4 instruction accesses plus 3 data accesses, right? That's what this program is going to generate. 2 reads of memory, 1 write, right? So memory performance is important. You see it can be easily on par with the instruction. If you remember the latencies I show you, then we talk about and the power, so you would see that it becomes more important than compute. Yeah. So factors that affect choice of memory. The first one is obviously speed. Should be reasonably fast compared to the processor, right? Processor executes at faster speed, but if you don't supply it with data fast, it's going to just stall. So why is DRAM is used? So let's look at this graph here. So this graph shows the cost versus access latency, and this is trade-off curve. So flip-flops is here as the lowest access latency, but the highest cost, right? Then you had SRAM, right? That had slightly higher latency than flip-flops, but the cost is cheaper, so that people like to use SRAM. Then there is DRAM somewhere in this curve, flash and disk. Flash was not here for a while, like it's relatively recent addition. For a long time, it was just that. And the reason why DRAM exists, it has a nice sweet spot on this curve. So if you can go in this direction, you get high access latency and higher cost. And I give you some reference numbers before on the cost and capacities you can get. So DRAM happened to have a good sweet spot on this curves of different trade-offs, right? That's why people use it. So it has a favorable point in the trade-off spectrum. And we as a programmers tend to write programs that require a lot of memory, so capacity matters a lot, and cost per dollar. Another question, why is DRAM fast enough? So as that student from Stanford said, 15 nanoseconds per request. Is it a lot or is it not a lot? It's how fundamental it is. So let's think about it. If you take an Intel chip of 3 gigahertz and we can execute 2 instructions per cycles, there's about 300 instructions I can do while I'm doing 1 DRAM access, right? So if I had 4 cores, this is how many independent programs I have, and each of them can generate at least 1 access, right? So you can try to serve them in parallel if you're lucky, but the latency is not going to go away anyway, right? So fundamentally, this core per request latency is going to stay there. So parallelism can help to overlap some extra latency, but latency still will be there, right? So it's not easy to hide it, right? Okay, why is this latency the way it is? To understand that, we need to understand the DRAM internal organization. Okay, so let's see what is inside DRAM. So inside the DRAM, and this is like real photographs of from the companies like Chipworks of the real piece. Like a lot of you probably have seen the DIMMs right before, not necessarily exactly the same DIMM, but still. So whatever you see here, right? This thing here, this chip, right? This is called DRAM chip. It consists of things called banks, and in between there is a peripheral logic, right? So each bank, it consists of a lot of different small rectangulars. Those are called mats. Each mat consists of a bunch of cells, right? So this is just to get you to understand what the terminology is. You soon will understand why there's so much hierarchy in building DRAM. The way we access the data, there is a word line driver, and there is sense amplifier that allows us to sense amplifies the information from individual bits. And we go into that in a lot of details. So, but this is at high level, how the memory is built to the smallest possible piece of it, which is called cell, right? The memory cells. And we'll look at the memory cells before. So let's look at it again more carefully. So at a very high level, what the memory element or cell is, it's a component that can be at least in 2 states, 0 or 1. That's what we fundamentally want to have. It can be electrical, magnetic, mechanical, it doesn't matter, but fundamentally it stores information, 0 to 1. So DRAM has a capacitor. So the capacitor, the best way to think about is a bucket of electric charge. You charge it, the voltage level indicator shows like what it is, but this is not part of the circuit. It's just an indicator. So don't think that this is a part of the circuit, say. Okay. So when it's full, it means it's charged. If it's empty, it means discharge, right? Okay, so what is DRAM chip and how it's built? So DRAM chip contains of billions of capacitors, also called cells. So every little like blurry pieces here are those DRAM cells. But the question is like, what is this thing in between, right? I try to zoom in, right? So those are DRAM banks. This is why there is some separation there. If you're going to use a magnifying glass and look at the chip, you're going to see these banks there, physically existing there. So what is this thing here? Well, you can see the thing. This is peripheral logic that helps to read, but you can see things can be distant from the border. It means that the latency can vary fundamentally, but they read from here or from here, right? So it means there are some challenges potentially that exist that we need to deal with. Let's see how we deal with these challenges. There is a thing called sense amplifier that essentially helps to amplify the charge. So it sends there some variation in the charge like that. Usually things are not fully empty. They're in some intermediate states. And sense amplifier amplifies the difference. It helps to convert what was nearly full to full and what was nearly 0 to 0. So we really amplify the charge. That's what sense amplifier does. And we had to deal with sense amplifiers because DRAM cells fundamentally leak charge. If you leave them unattended, they're going to leak charge. They're never going to be fully full. So this is a stable state. Okay. So how we can read something from a cell that is built based on the capacitor? So it has a connection to sense amplifier, and sense amplifier is essentially charged at half the max VDD. So when I'm going to connect the DRAM cell with the sense amplifier, I'm going to start to lose charge. Remember the best way how I'm teaching my B58 class right now, or 258 in downtown, computer organization class. It's like thinking about the water tank, right? The water is right at the top, right? And if you let it go through, if you open the gate, it will always go from a higher potential to lower potential, right? The same with charge, right? It has to start to lose the charge. It's going to lose some, so some of the charge is going to go there, and it's now going to, have this delta in its charge, sigma, sorry, and then you amplify the difference. And when you do that, you access the data. So you read what the data was there after amplification, sorry. So amplifier would get this to the state, and that it's going to tell you what the value you read, like 1. But then you see what the problem with the read here. It's destructive to a certain point, right? After I read something, I lost some of the charge, right? So I need to restore it. So I need to spend time on restoring the charge, right? Without that, the information with DRAM cells will get lost after the read. So reads is partially destructive, right? They lose the charge. Okay, so essentially, let's make another step of complication here. How we're going to read things, specific bits. We need to have the address bits from the address. Pavel has a question.
Yeah, I have a quick question. So it reads, it knows which value it read, and then based on that recharges, right? Either recharges to the full or drains, right?
Right now, there's address bits. I just showed you fundamentally how you read. Now I'm going to show how you know exactly what to read, right? So how to know the read to write bit, yeah. But yes, this thing knows how to amplify the charge. So it's over the half. It needs, and you need to fix it to the top. Yeah. Okay. Then from the address, you had a control logic signal that tells you whether to, connect this wire or disconnect it, right? I need a read this bit or doesn't need. And we usually write simplify this like big circle here, right, on the chip, and DRAM cell is drawn as a small circle. Okay. So now, after we look into this small and big circle, we're going to use them schematically, and let's look at how they exist. So like one problem that exists is that sense amplifier and address logic is way larger than the DRAM cell. So I cannot afford, if I want to get good density of the memory, to have all this logic for every DRAM cell, right? It would just make my memory ridiculously expensive because for every, I don't know, for every memory cell, we're going to use 10x more transistors to amplify it and bring an address to it, okay? So what is a compromise an architects came up? Of course, it's sharing, right? So I'm not going to have all of that for every bit. I'm going to have some form of sharing. That's a compromise to keep it cheap and to deliver the right capacity. So cost amortization. So essentially, each sense amplifier is not reading one, it's just reading multiple things. And this is the way we organize the memory. This vertical line is called bit line. This horizontal line is called word line. So essentially, whenever we look at the smallest piece of the DRAM organization called array or mat, what happens is when we read the whole row, right? What happens is those are the bits stored in my cells. Those are amplifiers connected with the bit lines, right? You see those are bit lines, right? And this is a word lines. So, so the way what happens when I know from the address, I need something from the column N, right? And the row M, this is the bit I want. So what happens, I do word enabler, right? So there is that connection that happens here. Then the charge sharing happens, right? So what's going to happen, because I'm going to do all of that, all of these guys start to lose some charge, right? Because I can only read them all together, right? So they all needs to be some restoration. And the bit here are going to go into this state. Then they're going to be like closer to 1/2 or further away to 1/2. Then I'm going to involve sense amplification. And the values here are now reflect that was in that row. While in that row, we are not sure what it is because it's not restored yet. Okay, so all the values from this whole row is now here. Okay. Then I can use the bits of the column and I read the bit I really need, right? And then I'm going to do charge restoration. And then I do word line disable. So I stop the leak charge from the row that I just fixed, right? Filled with the charge. Okay. And we restore sense amplifier again to 1/2. So I read the bit I want, I restore all the information, sense amplifier is ready for the next cycles. The thing I want you to remember here, you see there are distinct stages in the operation of DRAM. And as we see soon, each of them has certain latency, and those latency kind of add up, right? So when people ask you about fundamental latency of DRAM, it all comes from these different stages. I'm going to now formally define it for you, tell you why they have certain latency, but fundamentally that's what happens. DRAM needs to amortize cost of reading latency. So he needs to do some sharing. So it might manipulate more bits in parallel that it really needs, right? So that, and even with that, there's still some, latency cost to it. So you can, so what it leads to, you can come up with a better technology than DRAM instead of latency, but it's going to be much more expensive, right? That's where the problem comes from. So it's a trade-off. So that Stanford student want to reduce 50 nanoseconds, but he wants the cost of DRAM he's paying right now. If we're going to offer him 25 nanoseconds, but at 10x cost, he'd probably say no, right? So that's where the problem is. Okay. Okay. So how do we build a DRAM bank from the small DRAM arrays that I just showed you? By the way, DRAM, even DRAM array terminology, it's something that I think we come up with CMU because like Samsung was building things this way, but they never released the information until we actually look carefully and try to understand how the DIMMs are built. So it's not even like bank and chips are standard terminology people use for many, many years, but DRAM array is something relatively recent from, I think, 2012. And raw hammer, again, that's something they were, I believe they know about that the problem exists, that they never openly talk about it and mention it until we just reverse engineer and find that the problem exists. Okay, so what is a single DRAM array? So where this problem comes? So the problem comes is how many things I can have connected through a single DRAM array. So remember the sense amplifier, I want to amortize the cost, but how many of the cells I can have altogether? So what if I had 10,000 or more rows going this way vertically, right? From here all the way to here. So what's going to happen? Well, if you had a very long bit line, so this is your bit line, right? If it's very long, it becomes very difficult to sense data in far away cells, as we've seen here, right? If you ended up dealing with that, you will need some compromise because the latency becomes just prohibitively expensive. So what we do is we have banks. So the banks is essentially the slicing here. So when you look at that picture of the real DRAM, and this is a picture of a real DRAM, this is boundaries here between banks exist because there are a lot of sense amplifiers here. And I have to design it this way because if I'm going to make the bank even larger, my latency becomes too bad. So I need to find a good compromise, how frequently I reuse my sense amplifiers and replicate it because they're expensive versus how high is the latency. It's an endless game of trade-off, right? So I would love to have sense amplifier for each cell, but then I'm going to, like everything will be just filled with sense amplifiers. Cells are going to be very scarce, but I cannot just use one sense amplifiers for everything because then my latency is ridiculous. So in a sense, if you ask whether DRAM latency is fundamental, it's fundamental in the sense that it's a sweet spot of a trade-offs between different dimensions in the design, right? It's not specific that 50 nanoseconds is the smallest possible you can do with existing transistor technology, but that's the best sweet spot in terms of trade-offs across many dimensions, such as performance, power, latency, and cost. And there are 4 or 5 extra dimensions that I'm less familiar that Micron and Samsung use in the evaluation. Okay, like stability to failures, like different types of physical drifts that I don't even understand. I don't want to print like all these different quantum effects that happens to cells. This is something I'm not going to go to, but even this key for matrix already makes it complicated. So in a sense, it's not fully fundamental, but it's not a random choice either. It's a carefully selected trade-off between different dimensions. And this little piece got a name called subarray. So these banks are built of these small pieces, right? And those subarrays, again, were not a literature term. This is something we defined in one of Yoongu Kim's papers. Okay, the summary of DRAM operations. So whenever we access the chip, we goes to the right bank. We had row M and column N, and that tells us how to read the data. We have row address, so we know where to go. And then we know how to use sense amplifier to read the bit we want. Then we know how to access the column. The columns gives us the right bits into the value we want for the bit we want. And we close the row and restore everything. Okay. So essentially, at the very lowest level, DRAM is at the end of the day is a collection of subarrays. This is the repeated piece that is scattered across all of DRAM, subarray. Subarrays build big arrays, arrays build banks, banks goes into chips, and chips go into DIMMs. So a lot of levels, but now I hope you understand what they are, right? So it's not tricky, and you understand they're not done by some weird engineer. Why you had 5 levels of indirection here? So it just happened to be the good trade-off. Okay, so let's see how much time we have. We have around 15 minutes. Any questions about here until I briefly talk about some of the existing solutions? Pavel, go ahead.
So that's why when you showed us the energy requirement, it's because of this need to charge, recharge all the time?
Yeah, so that plays a big role. Charge, recharge, refresh, and also the fact that you need to access multiple things all together. That's part of the problem, right? So I want to read maybe 1 bit, but I had to read the whole row with that bit, right?
Aren't reads usually done on like a per word level or something anyway? Like
we'll get to that. So things are a bit more complicated, but to optimize the latency, usually their bits of your value are not necessarily stored consecutively, right? They might be scattered around, right, to improve parallelism.
Yeah.
Usually, how many cells in a row?
How many
cells? Yeah.
So that's very design specific, but we are talking. So there is such a thing called DRAM row. DRAM row is a parameter that's defined by the GDAC spec, and the typical numbers like 8 kilobit. 8,000 bits. Okay, don't ask me why specifically that, but that's
so if the CPU wants to access for example 8 bytes, it will activate the whole row to
You're
fix the
absolutely correct. So there is a reason why things are organized in pages in operating systems. That's not only because people in an operating system like it in a certain way, it's dictated by how DRAM operates. So DRAM, you cannot really, I might be a little bit incorrect here, but you cannot, if you want to read 1 byte from DRAM, there is not such thing as just reading 1 byte. You would have to activate 8 kilobit of information, and then you read a piece of it. Then remember, there's a cache hierarchy. Cache hierarchy doesn't let you to read just 1 byte. You're going to read a critical word first, which is either 4 or 8 byte, depending on your system, and then your cache wants 64 bytes, so you're going to get the rest of the 64 byte as well. So whenever you read 1 byte, a lot of things happens under the hood. So you bring 4 or 8 byte first to the chip, 64 byte to the cache hierarchy, and then you activate the whole blown DRAM row in your DRAM. Obviously, people who design DRAM are not stupid, so they know that activating, deactivating DRAM is costly. So they don't necessarily close the row right away. There are smart heuristics that if you see that there is a next DRAM access coming next, and it comes for the same row, they don't close the row, they keep it active. So you can keep it read it much faster from the same row. So if you had a high locality of your accesses, your memory latency tend to be 3x faster than, say, if you jump randomly across different DRAM rows. And memory controllers are smart enough to, when you had multiple cores, they can easily mess it up, this locality. So memory controllers are smart, well, modern memory controllers. The first memory controllers had bugs with it. But when the multi-cores was introduced, and there was like even denial of service for some cores. But essentially, the smart memory controller would see the traffic coming from different cores. It'd see whether accesses come to the same rows, and then it might prioritize things coming to the same row. Sounds like a good idea, right? It would improve the latency. The problem is that if you do that and you don't think about fairness, what might happen, you're going to always prioritize the cores that had good locality, and the thing that has poor locality is going to get denial of service. So there are some complications here, as you can see quickly, but the short answer to the question, yes, you're going to read a lot of redundant stuff. So if you ever be asked a question, why the latency of DRAM versus processor or cache is 10 to 15 or 20x, but the power energy is 3 orders of magnitude, this is because of that. It's because we have this organization that is a compromise, and I burn a lot of power to do it. Okay, any questions?
Just a quick question.
Go ahead.
Do you think maybe 3D stacking will do something for this? Will be able to help in any way?
Fundamentally, 3D stacking, I don't really cover in my class. I'm going to maybe touch briefly. It helps certain things. Like the only thing that 3D stacking helps is bandwidth, which I'm not even touching right now. We didn't reach this stage yet. So there would be a other dimension of complexity, which is DRAM bandwidth and how much things I can read in parallel. And that's what 3D stacking comes, and like some thermal issues as well. But no, 3D stacking, people frequently confuse. They think 3D stacking is going to solve the latency. No, actually 3D stack memory has worse latency because you get through an extra layer of indirection. Okay, any other questions? Okay, let's go at least through some relevant papers. So factors that affect performance. So latency, how fast can DRAM serve a request, and parallelism, how many requests can DRAM serve in parallel. So we just went through this organization. So this is the latency, this is the parallelism, right? And here are a couple of techniques that some of them I help significantly, some of them I didn't really help, but this is some solution that exist. So one of these techniques is trying to do trade-off within subarray itself. So if we look at subarrays, and now you all understand what subarray is, right? I hope you understand that's the smallest unit at which you iterate. Again, you're not going to see this term in Samsung or Micron literature, but what they really built, they had some internal name, that the name we gave it, and that sticks in computer architecture field. So essentially, what is the trade-off here? So I can have small subarray or larger subarray. What's the trade-off? Shorter bit lines means fast access. Smaller subarrays means low access latencies. But essentially, you understand that the cost and density changes, right? Because you need to have more sense amplifiers. So if you look at the chip area, if I had smaller subarrays to get the same amount of useful cells, so the blue, the blue shapes here, right? They don't really store any information. They have peripheral logic to read from the green cells. So if you look, the number of green cells here and here is the same. So it means in the large subarray design, I had way more efficient representation than in a small subarray, right? So you see the problem, right? I want smaller subarrays for latency, right? But they are way less efficient in terms of area cost. So smaller subarrays leads to larger chip area. So one of my collaborators, Don Hugh, asked the questions, can I get both at the same time in one design? So can I get some interesting design where I can get, don't pay the cost of a large chip area, but I still get low latency. Mustafa?
Yeah, so I was just remembering something you were saying like earlier. So right now we're talking about like whenever you something from RAM, like you read it, then you like read the value, then you amplify it, and then you refresh the thing once you're done reading it. But I remember like you were talking about like I guess in last lecture, like how the refresh times of chips changes, and you were saying like Apple decided to refresh their chips faster. Like how do you do that then?
So that's a little bit orthogonal to, I'm not going to cover it today. So essentially the way refresh is implemented, that's there's a parameter that right now is programmable. You set it, and essentially operating system periodically refreshes things. It's not directly related to what I'm going to talk right now. This try to cut latency. Refresh is an orthogonal thing related to the fact that the charge leaks. So even if I don't read or write, I don't use DRAM, charge still leaks. I still need to refresh.
I see.
So whatever I'm going to do right now is not related to refresh directly. Refresh is an orthogonal problem. Like a lot of this technology has multiple related things and unrelated. So the refresh rate won't be a player here.
Makes sense. Thank you.
Okay. So what is the real trade-off? So this is results Don Hook collected because he actually spent like 10 years of his life at Samsung. He knows a lot of how these things are built. So here is the normalized chip area versus access latency. So if I would use 32 rows per subarray, my latency would be closer to 20 nanoseconds. So that's how much room. Commodity DRAM use 512 rows per subarray, right? So someone asked about how many data we have. So that's how much you have per subarray. So you see, this is slightly over 50 nanoseconds, right? That was referenced by the Stanford student. Anyway, we're coming back to this question, why DRAM is so slow? Because we pick this as our commodity choice. Can we do better? Well, we have some room for improvement, but the problem, normalized chip area. So this 2.5 reduction in speed and latency, increase in speed, reduction in latency, come at almost 4x increase in cost. Okay, so you see it, right, guys? Okay. So the question is, can we enable any beta points on this curve relatively cheaply? And what Don Hook essentially proposed is a cheap way to get large subarrays. So instead of connecting every little piece through sense amplifiers, he connects them through smaller pieces here, right? So those are simple wires that just do activate, deactivate, but they don't do sense amplifiers. How would this work, and why does it make sense? So essentially what he proposed is a so-called tired latency DRAM. DRAM in which the latency used in near and far segment of the memory can allow to have different latencies. So in the far segment, you had higher access latency and higher energy access. If you disconnect, right, then you cannot read that memory there. And you're going to have less memory, but with low access latency and lower energy per access. So essentially, you have just a simple connect-disconnect circuits here. You don't need to have a full-blown amplifiers here, but the memory loses its unique access latency. So he built this substrate. The question is how I can benefit from it. So what would you think? What could I do if I had memory of two types, faster and slower?
Use the faster memory as some sort of buffer for the slower memory?
Yeah, cache.
Like that?
Essentially, we were building caches before from a faster memory. So if I can get a faster DRAM, but remember, it's smaller, but it's small in DRAM terms. We're talking about gigabytes here. So I can get gigabytes of SRAM at a very small gigabytes, of cache, but not using SRAM, using DRAM commodity technology. So an SRAM, I won't be able to afford it, right? So essentially, we map frequently accessed data to near segment. So what we're going to get, this is just average numbers collected across many applications. You don't need to go into each application. What's the key thing here is that proposed tight latency DRAM, where we propose to use a short, small segment as a cache, has better latency for those frequent accesses. So it allows to improve performance and it reduces energy consumption significantly, right? So it turns out to be a good design in both performance and energy. So 12% on average, 23% in energy consumption. Remember, this is general across all apps. So in computer architecture, numbers are usually not 10x or 2x. So like the whole team at Intel designing cores would work for 2 or 3% speed up from generation to generation, right? So you get a feeling what it is. So for them, this is a huge speed ups from memory. From memory speed ups, from big advantage, in, like if you had optimization that generic across all different, applications within memory, double-digit speed ups considered to be very good, right? In terms of percentage. Okay, and that's if you want to read the paper. This is the paper on tight latency DRAM. Okay. Okay. And I think I don't really have time to go into anything else today. So I'll just stop there, and in the next class, I'm covering another 2 pieces of work. Okay. Any questions, guys, about today's lecture on caches, memory, project proposal? Is everything clear? Okay, I hope it was not too dense today, so you learned a lot of useful stuff about DRAM. I hope now, when you're going to think about memory operation, you would really, really understand how it works, right? I try to, like, it's usually considered to be very complicated topics. Remember when we wrote the first few papers on DRAM like that? One of the biggest compliment we get from reviewers was saying, oh my God, I finally read the paper that clearly explained how DRAM operates. Because before, everything was very kind of indirect or hidden. So people didn't really, even the people who work on it didn't understand. And what helped is, good writing and someone who work on their, like we had these 2 guys, Don Hook and Yungu, who in Korea work in Samsung. So they really understand how things done at the bottom, right? So the ability to write well combined with a deep knowledge of the organization of DRAM help, to discover not only, some interesting problems in DRAM, but also teach the community about how good is, how the DRAM operates. So I think I got a question here. Okay, I see. Okay, thanks, Mustafa. I treat it as a compliment. I treat it not as it was super dense today. Okay. Any other questions, guys? Comments? Okay. If there are no questions, I think we're done today. Thanks a lot, guys. And yeah, so if you had any questions, send an email to me or TA or post something on Piazza. Thank you. And good luck with your proposals.
Thank you.
Thank you, guys.
Thank you.
Yeah. Have a nice week. Bye.